multicollinearity. So in this topic, we will learn about perfect and imperfect multicollinearity, effects of multicollinearity, how to detect multicollinearity, and also remedies for multicollinearity. So for multicollinearity, we are looking into the relationships among the independent variables, the x's. So when we talk about perfect multicollinearity, meaning that we are saying that there are some functional relationships exist among the independent variables. So suppose we have this kind of relationship whereby x1 is equals to minus 2x2. So meaning that once we have x2, we will straight away know what is x1. So here we have a perfect relationship between x1 and x2, and we can rewrite this expression into 1x1 plus 2x2 equals to 0. So with this, we have a general form of defining perfect multicollinearity, whereby it is when there are some functional relationship exists among independent variables, that is the summation of gamma 1 gamma I xi equals to 0, or it's the same as gamma 1 x1 plus gamma 2 x2 until gamma m xm equals to 0. So if we can find gamma 1 until gamma m and equals to 0, means that it is a perfect multicollinearity. So when we have a perfect multicollinearity, what happens is the regression coefficients of the xi, which is the betas, are indeterminate. So we cannot determine the values of or the estimates of betas. And also their standard errors of betas are infinite. So suppose we have two independent variables, which is x2 and x3. So this is the model y hat equals to beta 1 hat plus beta 2 hat x2 plus beta 3 hat x3. So this is the formula to get beta 2 hat. So suppose x3i is equals to lambda x2i. So this shows is a perfect multicollinearity. So when we replace x3 with lambda x2i, what happens is that we can cancel out all the terms and we get 0 over 0. So when we get 0 over 0, meaning that we cannot determine beta 2 hat, so meaning that it is indeterminate for beta 2 hat. This is similar goes to beta 3 hat. And for the variance for beta 2 hat, so this is the formula for variance beta 2 hat, whereby we have this sigma squared over square root of x2i squared 1 minus r23 squared. So if we have a perfect multicollinearity between x2 and x3, so R23, which is the simple correlation coefficient between x2 and x3, will be 1. So if R23 is 1, then R23 squared will be 1. So 1 minus 1 will be 0. So we get something over 0. So when we get something over 0, means it's undefined, so or it means infinite. So we have this infinite here. So this is an example of y regressing on x1, x2, and x3, and we have x2 equals to 5x1. So this is a perfect collinearity, whereby once you know x1, you will straight away know x2. So here example x1, you have 10, 15 until 30, so you will straight away know x2, whereby it's just multiplying with 5. So this is a perfect collinearity between x1 and x2. So suppose y is our output, x1 is our capital, x2 is labor, and x3 is length. The second example is y on x1, x2, and x3, whereby x1 is the nominal interest rate, x2 is the real interest rate, and x3 is CPI. So we can suspect that there will be a problem of multicollinearity, whereby in order to get real interest rate, it's just simply between nominal interest rate and also CPI. So you already take out the the inflation from nominal in order to get real interest rate. So there will be a collinearity between these two variables. So the third example is y on difference of xt and xt minus 1. So the delta xt here is usually defined as xt minus 1. So once you have the first difference here, why is it called first difference? Because it's an xt minus 1. It's like 1 year. So if it's like 2 years, then it's going to be the second difference. So when you have the term first difference here and you have the original term, which is xt and xt minus 1, definitely there will be a collinear relationship between these variables. So this is an example of perfect multicollinearity. So please take note that this is considering linear relationship between x's. So suppose we have x2 is x1 squared. Okay, because it is fine to have a squared terms in the equation. So if you have this x2 is actually x1 squared, then x1 and x2 is not a linear relationship, it is a quadratic relationship. So with that quadratic relationship means that it doesn't fall under perfect multicollinearity. It is okay to have a squared term inside the model. So when we talk about multicollinearity, perfect multicollinearity, we are referring to the linear relationship among the axes. Imperfect multicollinearity refers when some independent variables are linearly correlated, but the relationship among these independent variables are not exact, meaning that it is not exactly example x2 is 5x1. Okay, so maybe x2 equals to 5x1 plus stochastic error. So when we look into the formula for beta 2 hat, this is the formula to get beta 2 hat. And suppose we have imperfect multicollinearity whereby x3i is lambda, x2i a value of lambda plus vi. So this is the stochastic error, meaning that it is random here. Okay, so when we replace this x3i with lambda x2i plus vi, replacing everything beta 2 hat, we won't get 0 over 0. It will be something not equal to 0, meaning that we can get the estimates. So even though the regression coefficient, whereby it is the beta 1 hat, beta 2 hat, beta 3 hat, and so on, is determinate, the problem is it possesses large standard errors. So when you possess large standard errors, meaning that the coefficient that we estimate is less accurate or less precise, because precision of the coefficient, it depends on the variance or the standard errors.